All right, let's get started. As a communications engineer, one of the first things you'll really have to get your head around is how to build a bridge. Not a physical one, but the one that connects our rich, kind of messy, analog world to the clean, precise digital universe. Honestly, it's the foundation of everything, from your phone call to streaming music. Let's dive in.
This right here, this is the fundamental question. I want you to burn this into your brain. Think about it for a second. A human voice, the sound of a guitar. These things have infinite detail. But our digital networks, they only speak one language, ones and zeros. So the first massive problem we have to solve is, how do we translate the poetry of an analog wave into the rigid grammar of binary?
Okay, look here. On the left, that's the real world. See how it's a smooth, continuous wave? Every single point in time has a value. Now, on the right, that's what our digital system gets to see. Just a series of discrete snapshots. We call them samples. Our entire challenge, really, it all boils down to taking these snapshots in just the right way so we can perfectly rebuild the original wave on the other side.
So here's our game plan. We're going to start with the most critical first step, which is sampling. Then we'll look at how to encode those samples using pulses. After that, we'll build the entire pulse code modulation, or PCM pipeline, and we're going to really dig deep into quantization. We'll touch on some advanced tricks, and then finally, we'll put on our system designer hats and see how this whole thing fits together.
Okay, first up, sampling. And let me be clear, if you get this part wrong, nothing else you do is going to matter. The entire system will fail before it even gets off the ground. This is where we learn how to take those snapshots intelligently.
And this is your golden rule. This is the law of the land, the Nyquist theorem. It's simple, but it's non-negotiable. It says your sampling frequency has to be at least double the highest frequency in your signal. So, for human speech, which tops out around 4 kilohertz, we sample at 8 kilohertz. For CD quality audio, with frequencies up to 22 kilohertz, we sample at 44.1. This isn't just a good idea, it's a mathematical requirement for perfect reconstruction.
And this visual shows you why that rule works so perfectly. On the left, that's the frequency spectrum of our original signal. When we sample it correctly, look what happens on the right. We create these perfect, clean copies of that spectrum. You see that gap between them, that little bit of empty space? That's everything. It means we can use a simple low-pass filter to just pluck out the original spectrum and rebuild our signal flawlessly.
But this is what happens if you break the rule. If you sample too slowly, those spectral copies, they crash into each other. They overlap and get smeared together. We call this aliasing. High frequencies pretend to be low frequencies, and you get this awful distortion that is fundamentally impossible to remove. I mean it. The information is permanently destroyed. It's one of the first, most painful mistakes a junior engineer learns to avoid.
So, we've taken our samples. Each one is a snapshot in time, but it's still just an analog voltage level. We're not at ones and zeros yet. We need a way to represent that value, so this is sort of an intermediate step, a bridge to get us closer to our goal. Okay, check out these 3 techniques. We start with a simple, boring train of pulses. With pulse amplitude modulation, or PAM, we just change the height, the amplitude, of each pulse to match our sample's value. Super simple. With pulse width modulation, PWM, we vary how long the pulse is. And with pulse position modulation, PPM, we actually shift the pulse's timing back and forth. You see, it's 3 different languages for encoding the exact same piece of information.
So which one do you pick? Well, like everything in engineering, it's always about the trade-offs. PAM is the simplest to build, but since all the information is in the amplitude, it gets clobbered by noise. Now, PPM is the most complex, but it's incredibly tough against noise, because the receiver only cares about when the pulse shows up, not its shape. As the system designer, you have to weigh these things: cost, complexity, noise, for your specific application.
Now, pulse modulation is clever, but it's not truly digital. The values are still continuous, they're still analog. To get to pure binary, we need the industry-standard workhorse pulse code modulation, PCM. This is the complete system you'll find at the heart of pretty much everything, from WAV files and CDs to modern digital phone calls.
I want you to think of PCM as a 3-stage assembly line. First, we sample the signal. We already know how to do that. We just follow the Nyquist rule. Second, we quantize. This is where we have to make an approximation, and we'll talk a lot more about that. And third, we encode that approximated level into a binary word, a string of ones and zeros. This is it. This is the process that turns a real-world wave into pure data.
All right, let's hit pause for a second and really zero in on that middle step.
Because quantization is truly the heart of the analog to digital conversion problem. This is where the real engineering decisions are made. It's where we have to balance quality against efficiency.
So here's the crucial point you have to accept. Your analog sample can have an infinite number of possible voltage values, but if you're using, say, an 8-bit system, you only have 2 to the 8, or 256, binary codes to represent them. So you must approximate. You have to map the sample's true value to the closest available digital level. This process creates a small error, which we call quantization noise. It's the price we have to pay to go digital.
So how do we choose our levels? Well, the simple way is uniform quantization, where every step is the exact same size. You might see this in a high-end audio workstation where you need absolute signal fidelity. But for signals like speech, it's really inefficient because most of the signal is actually pretty quiet. A much smarter way to do it is logarithmic quantization, where we cram more levels into the quiet regions and use bigger, coarser steps for the loud sounds that our ears are less sensitive to anyway.
And these curves show you exactly how we do it. These are standard compression laws. Mu law is used in North America, A law in Europe, that define these non-uniform levels. Look how steep the curve is right there in the middle. That means a huge range of quiet input signals get mapped to many, many different output levels, which preserves all that subtle detail. Then as the signal gets louder, the curve flattens out, dedicating fewer levels to the loud parts. It's a system that's literally tuned to how humans hear.
Let that sink in for a second. By being clever about how you quantize, you can get the same audio quality with just 8 bits that a naive system would need 10 or even 12 bits to achieve. That is a massive saving in bandwidth. And it all comes from one single insight: understanding the statistics of your signal. Remember that. That's the secret to smart communication design.
But you know what? We can be even smarter. A good engineer gets the job done. A great engineer, once they have a working bit stream, immediately starts looking for ways to squeeze out every last bit of redundancy and optimize it. Let's see how.
Take a look at differential PCM, or DPCM. The big idea here is that most signals, like audio, don't just jump around randomly. They're highly correlated. The value right now is probably very close to the value it had a microsecond ago. So instead of sending the full value every single time, DPCM predicts the next sample and just sends the small correction, the difference. And since that difference is usually a very small number, you can encode it with way fewer bits than the original sample.
Okay, time to zoom out. We've been deep in the weeds with sampling, quantization, encoding. Now let's assemble all those pieces into the complete end-to-end communication system that you'd actually go out and build.
Here it is, the full chain of command. You start with your analog source. You sample it, making absolutely sure you avoid aliasing. You quantize those samples, choosing a smart strategy like logarithmic mu law for efficiency. You encode those levels into binary bits, but you're not done. There's one final critical step before you can actually send that data down a physical wire.
You have to prepare those raw ones and zeros for the physical world, and that's the job of line coding. You can't just send a high voltage for a 1 and a low voltage for a 0. Why not? Well, what if you have a long string of zeros? The receiver's clock might drift and lose its timing lock. So we use clever line codes like these to shape the electrical signal, guarantee clock transitions, manage the DC power on the line, and shape the signal spectrum to perfectly fit the channel it's traveling over.
And this, right here, is probably the most important lesson I can give you today. From your sampling rate, to how many quantization bits you use, to the line code you pick, every single decision is a trade-off. You want higher fidelity? It's going to cost you more bandwidth. You need to save battery power on a device? Well, that probably means a simpler system that might be less robust to noise. A systems engineer lives in this space, constantly balancing these competing demands.
So I'll leave you with this question to think about as you start your career. In a world where bandwidth feels almost infinite and processing power is dirt cheap, are all these clever tricks for saving bits still as important? Or have the goalposts moved? Are the critical trade-offs for your generation of engineers going to be more about latency and energy efficiency instead? That's the problem space you're going to be solving.